Hello, everyone, and I'm honored to have the chance to share my work. My name is Qingyue, and I come from Hunan University. The title of my presentation is Knowledge-Augmented Dynamic Neural Network Model and its application in credit evaluation. There are five main aspects. Sorry. There are five main aspects to this topic, starting from the introduction of this work, and then give the fundamental knowledge in the preliminary section. Then I will introduce our method, and next, I will show the results of our experiment. Finally, I will conclude this work. Let's start at the very beginning. With the transformation of financial consumption patterns, there has been a rapid increase in credit demand from small businesses and individuals. In order to cope with this trend and effectively manage risks, various types of lending institutions urgently need to establish accurate and efficient credit assessment models to optimize the credit decision-making process. However, despite the importance of credit evaluation, we still face many challenges in practice. These challenges arise from two aspects. One is the inadequacy of data or data quality issues, and the other is the limitations of traditional credit evaluation methods. The data for most small and micro enterprises cannot be guaranteed in terms of data quality and authenticity of data due to their small scale, weak capabilities, and imperfect management systems. Moreover, the diversity of industries, regions, cultures, and business characteristics also poses challenges in obtaining relevant business information for credit evaluation. Moreover, in the face of various new credit business or new customer groups, the existing credit evaluation model may not be applicable, but there is a lack of available historical data to initialize the new model. In this case, credit assessment models relying on expert experience would be more appropriate. Analytic hierarchy process is one of the classical methods. This type of method is evaluates credit scores through subjective judgments of credit experts on the relevant factors that may affect the probability of default of a borrower. Therefore, the AHP model can rely on the experience of experts to build the model without relying on historical data. But the AHP model is subjective due to human cognitive bias and experience limitations. Statistical methods and machine learning approaches are objective and accurate, but they require adequate training data. Due to this limitation, some methods cannot be applied to new credit business or new customer groups and lack sufficient interpretability. Based on these observations, this work aims to combine the advantages of expert knowledge-based method and machine learning approach to overcome the limitations of existing methods and improve the accuracy and efficiency of credit evaluation. There are two goals. One is utilize expert knowledge to initialize models in the early stages of a business, overcoming the challenge of cold start problem. And another is to use machine learning method to make up for the shortcomings of expert knowledge-based method and improve the accuracy and the objectivity of credit evaluation. And now let's move on to the preliminary part. The Analytic Hierarchy Process, we call AHP, refers to the decision method that decomposed the elements that are always related to the decision into the levels of goals, criteria, alternatives, on the basis of which qualitative and quantitative analysis is carried out. The key steps of AHP increase to determine the goal and structure the hierarchical framework, and then construct the judgment matrix. Specifically, it decomposed the decision-making problem into different hierarchical structures according to the order of the overall goal, the sub-goals of each level, and the evaluation criteria and the specific alternative plans. Then, by solving the judgment matrix, the priority weight of each element in each level to the element in the previous level is obtained, and the final weight of each alternative plan to the overall is merged layer by layer by weighted sum method. This is this final weight maximal is the optimal solution. The next is the backpropagation neural network. This algorithm remains the most classical learning algorithm for neural networks. It operates in two distinct stages. The first is the forward process. It calculates the output values of each node layer by layer, while the reverse process calculates the error of each hidden layer node and corrects the connection weight with the preceding layer. A BP neural network refers to a feedward neural network that is trained by the BP algorithm. Given a network structure and initial weights, the BP algorithm repeats the forward and reverse process until convergence. However, it should be noted that the BP learning algorithm is a local optimization method, and it is easy to fall into local minima without obtaining the global optimal solution. Therefore, the network structure must be predetermined prior to training. This means that the layers of the network and the number of network nodes in each layer need to be specified. The second drawback is that the hidden layer lacks clear theoretical guidance, resulting in large randomness. Moreover, neural network models are less interpretable due to their black box nature. Okay, that's the groundwork. Next state the research problem and display the brief of our method. In the practice of credit evaluation, because of the differences of different customer groups, it is not appropriate to simply copy the evaluation model which suitable for one type of customer group to another. Therefore, it is necessary to create a graded evaluation model for new customers according to their characteristic. However, it is difficult to obtain enough business data, especially in the initial stage of credit work. There is no information about the customer, so it is not possible to use machine learning methods to build the model for credit evaluation. After a brief introduction to AHP and neural network, it can be found that the structure of them is very similar. Inspired by the structural similarities and respective advantages and disadvantages of neural network and the AHP, we try to combine neural network with AHP to solve this problem, the cold start problem. We propose a knowledge-augmented dynamic neural network model. We call it KADNN. In the field of machine learning and artificial intelligence, knowledge augmentation typically refers to the use of multiple methods, models, or algorithms working in concert with each other. And this fusion can reduce the limitations of a single model or algorithm in dealing with complex problems and increase the accuracy and reliability of the system in understanding complex relationships, making predictions, and making decisions. The KADNN model combines the advantages of the two approaches, using expert knowledge to initialize the model at an early stage of the business, can solve the problem of not being able to construct a credit assessment model without historical data, and realizes knowledge augmentation. The construction of the model can be summarized into three main stages, which can be seen from this figure. Firstly, in the initial stage, the AHP method is used to construct the subjective evaluation model of credit evaluation based on expert experience, and according to from this point on, credit evaluation work can be conducted, and business data can be accumulated. Then, according to the structure of AHP model, a neural network was constructed according to the structure of the AHP. And the AHP's weights were used as the initial weights of the neural network. So far, we can build an original simple neural network model. And after that, dynamically updating and optimizing this neural network model according to the continuously updated data, and previous models will achieve a more accurate and objective evaluation model. Okay, now I will introduce the key steps of our method. We first designed the model structure of KADNN based on the hierarchical structure of AHP. That is, the nodes and weights of KADNN are set according to the nodes and connection weights of AHP. However, there is a conflict. KADNN is a neural network model, so it is fully connected. But the upper and lower nodes of the AHP model are not fully connected. To solve this problem, we propose a modification to the network structure by introducing a connection matrix between layers. Each element, EIK, represents the connection between node I and node K. If the ith node and the kth node have a connection, then EIK equals 1. If no, then EIK equals 0. After the modification, the original formula for calculating the input value of the neural network nodes needs to add this element. By doing this, we solve the problem of blindly determining the neural network structure. And in addition, we directly determine the connection weights between nodes according to the AHP model's weights without needing to reassign them. This design avoids result instability caused by the random assignment of initial values, while providing actual meaning to each node's connection and weight, thereby improving its interpretability. Another optimized design lies in the fact that we have retained the use of activation functions while combining the features of AHP and neural network. In the AHP model, the outputs of the upper nodes are obtained from the weighted sum of the connected lower nodes. Thus, the output of the upper nodes is just a linear transformation of the lower nodes. However, in the neural network model, after the weighted sum of the lower nodes is derived, it also needs to be calculated by the activation function. That is, the outputs of the lower nodes are non-linearly transformed to the outputs of the upper nodes. This increases the complexity, but also enhances expressive ability. So the proposed KADNN inherits the characteristics of neural network and uses a nonlinear activation function, which increases its complexity, but also enhances the expressive ability to accurately represent the relationship between upper and lower element nodes. After completing the initialization of the model and solving the cold start problem, data accumulated from subsequent credit operations can be leveraged to update and enrich the network within the credit evaluation model. Next, I will present experimental results. We implement a credit evaluation simulation to demonstrate the application of the proposed method and validate its effectiveness. In our experiments, the KADNN algorithm is applied to the German credit assessment dataset. According to the specific meaning of the variables provided by the dataset, we establish a personal credit evaluation index system, and based on this index system, we obtain the relative weights of 3 hierarchies in the AHP model, shown in Table 1. Subsequently, the KADNN model is initialized using these weights from the AHP model. Finally, a non-fully connected neural network model based on the AHP model is depicted in this figure. And we compared the performance of AHP and BPNN and KADNN, these three models, to demonstrate the effectiveness of our algorithm. We have adopted three classical machine learning performance evaluation metrics, including precision rate, recall rate, F1 score, as assessment criteria for this experiment. The performance comparison of these three models is presented in Table 2. It can be observed that among these models, the AHP model exhibits a lower precision rate, recall rate, and F1 score. This suggests that a model based solely on subjective experience lacks discriminative ability compared to a machine learning model that leverage objective data. On the other hand, when credit data is limited, the KADNN model consistently performs well across different customer types, good customer, bad customer, and average, with its value being the highest among all three models. This demonstrates the advantages of incorporating both expert experience data and objective information for building robust models. Furthermore, in credit evaluation scenarios, it is more important to accurately identify bad customers, and the recall rate can reflect the ability of model in this regard. Although the recall rate of KADNN is slightly lower than BPNN's recall rate, it significantly outperforms the AHP model in this aspect as well. Finally, I will conclude this work. And the key contributions of our work can be summarized as follows. We present a new credit evaluation model that combines the advantages of AHP and the neural network to achieve knowledge augmentation. This model utilizes expert knowledge to initialize models in the early stage of a business, overcoming the cold start challenge of training credit evaluation model. Alternatively, the data derived from continuous credit operations can be leveraged to update and enrich the network within the credit assessment model through the application of machine learning and techniques. As a result, the defects resulting from subjective cognitive bias in the initial stage of the model are rectified. Finally, the proposed neural network model we construct is inspired by the structure of the AHP model. This approach avoids the problem of determining nodes in neural network design, while providing specific meaning to each node, thereby improving the comprehensibility of the model. And that is all my presentation. Thank you for your listening today.